Okay, I'll turn it
Yeah,
off.
yeah.
Okay.
Yeah. Co-host can record.
Okay, Rob, how can I turn that off? Pause, stop. There we go.
Got it.
Mike, say something.
Yeah, hi there. I'm here.
Okay, can you spotlight James, please?
Sure.
What on earth you got behind you? Egyptian art?
Does kind of.
Yes, I do. Egyptian art. I can give you a better view of it too.
Nice.
There we go. That's better.
Let's see, and then we can go to the Bhutan stuff.
Okay.
I was reading a book recently that was happening in Bhutan.
All right, I will, if we're all set here, I guess I will start the slideshow.
Yeah, so if you want to do that, Mike.
Although
You can start letting people in too, if you want to just open up the
okay,
meeting.
right. Yeah, okay, let me do that, right.
Got thousands of.
So what's, I'll introduce you.
Okay,
I'll make a few comments and then introduce you.
cool.
And then you can just take it away.
Sounds good.
Before we start the meeting, we have like this introductory slideshow that we just run as a loop.
Sure.
And so that's what Mike's going to do for everybody.
Okay,
And let
perfect.
them all into Zoom.
Perfect.
And then we're going to stop that at 6 and we'll start here.
Cool. And for the introduction, is there, I don't need to like hand this mic to you, do I?
No, I think.
There's a second one there, I guess. You could use that one and I could be quiet on this one.
But I'll be right here, so here, I think do you still have your computer mic on?
See, I don't know how that works. That's what I'm not sure about.
Yeah, I can. Not real.
Not real loud?
Right there.
Microphone. Oh, why not?
So far, we don't have anyone
You must be the
other than.
speaker.
the
I am. I'm
host,
James.
And
tonight.
I'm Gros Ventre
Oh,
aficionado.
nice to meet you.
Yes, we emailed it
I
yesterday.
tell you what, I hiked up there on Sunday, actually,
You what?
to Pack Saddle Pass. I
You
went up
went
there.
up?
I went up on Sunday. Yeah, I had a day off and kind of spurred by your email. I'd always wanted to do it.
What
So
approach did you go?
went up Granite Creek.
And then just directly? up?
Yep, there's an outfitter trail that takes off. It's probably about 6 miles up Granite Creek from the hot springs, and it leads directly up to the pass there.
So right when you're on the trail, you can see this?
Yep,
elevator
yep.
trail?
It's right. It takes off. You can actually see the outfitter camp. It's kind of across the creek on the left if you're
'Cause
looking
that's pretty
upstream.
steep.
It is steep. And it heads straight up. There's no switchbacks. It's real steep trail.
Yeah.
But it goes all the way up and over the
Well,
pass.
What did you find?
There, sure enough, there are a ton of quartzite, rounded quartzite cobbles, which could be coming from anywhere, but are likely transported. We see a bunch of those quartzite cobbles.
now
farther
sharing my
east and
screen.
north,
Can you see it,
kind of in the Continental Divide area.
Cynthia?
I think Ken Pierce postulated that those were coming from the Pinion conglomerate further north. I would.
What just happened here? Who's everybody? No. Oh, geez, what's going on here? What just happened? Is anyone? Hmm. I don't like it. Uh, can anyone in the auditorium? Should be okay. No.
Let's get over here, Dan. Mike, Cynthia, can you hear me? We're ready to start here in the library.
Yeah.
Wow, it's dark in here. I think we need a little bit of light. Got a lot of light. Okay. That's good. That's perfect.
You know,
I do, yeah. All right, hi, everybody. Just a sound check. Mike Adler, can you hear me?
Yeah, I can hear you. I can hear you.
Okay, great. Okay, thanks. So, hi, everybody, and welcome to the library, and welcome to the Zoom audience. My name is Cynthia Blankenship. I'm president of the Board of Geologists of Jackson Hole and co-chair of the Speakers Committee, for those of you I don't know. And as a reminder to folks here in the library, please mute your cell phones or turn them off. That would be awesome. And to folks on Zoom, Mike Adler is our Zoom host tonight. And so if you have questions, please send them via chat to Mike Adler. Thank you very much. And a few of our normal announcements. I think, as you all know, for more than a decade, we have been partnering with the Teton County Library and the Library Foundation who allow us to use this outstanding facility. And it's really great to be back in person again in the library. So thanks again for coming out tonight. And as you also know, our talks are part of the Science and Nature Tuesday evening programs. And I will say that since September of this year and going until next September, the library has allowed us to do one presentation a month. So instead of two, we're going back to one, and we have the first Tuesdays, as most of you probably figured out. But when that first Tuesday corresponds to a holiday or a voting day, we will try very hard to go to the following Thursday, so 2 days later, instead of the first Tuesday. So our next talk next month will be on November 1st. And again, it will be here at the library and via Zoom. And it's entitled Greater Yellowstone Climate Assessment, presented by Dr. Brian Schumann, the University of Wyoming. And that sounds like it should be an excellent talk, very important and local interest. So that would be great. And moving on then to tonight's program, I would like to introduce James Mauch. He and I actually met a few days ago. We were on a field trip together called the Friends of the Pleistocene, which was an outstanding trip locally here in Jackson Hole, mostly in the Grand-Teton National Park. And in fact, the field trip was in honor of the late Ken Pierce, and his daughter Jen was there, and so it was a really very nice trip. So back to James. So James grew up in Grand Junction, Colorado. He got his bachelor's in earth science from Montana State University and his master's in geology from Utah State University. His master's thesis focused on understanding the geomorphic signatures of Quaternary salt dissolution subsidence and river incision around Moab, Utah. Not a bad place to be. He has worked for the Wyoming State Geological Survey since 2019. He specializes in geologic hazards, mapping, and geomorphology. His current projects include surface geology mapping of the Ramshorn quadrangle and a landslide susceptibility study for southern Teton County. Outside of work, he enjoys exploring wild places via skis, bike, boat, or hiking boots. So thanks again, and help me welcome James.
Thanks, Cynthia. All right, thanks, Cynthia, for that introduction. And I will get my slideshow going here. All right, perfect. All right, great. Well, thanks to everyone for coming out tonight, and thanks those of you who are tuning in on Zoom. It's really an honor to get to speak in front of you all. I've been working with some of my colleagues from the Wyoming State Geological Survey up here in Northwest Wyoming for a few years, completing surficial geologic maps, and it's always gratifying to get to speak to a bunch of locals who know the geology and know the geography and interact with some of the features that I'm going to talk about on a frequent basis. So I'm really happy to be here. My talk tonight is titled Glaciers, Faults, and Landslides. And so these are kind of going to be the three organizing themes of my presentation. And I'm going to go over a few highlights in vignettes, if you will, of some of the geologic story that we've been working on while we've been mapping the Jackson Lake and the Ramshorn quadrangles. And you'll see on the title slide here, I have a photo taken from the Baldy Mountain area looking west at the Tetons. This photo was taken almost exactly a year ago. But I want to make it clear from the onset, I actually won't be talking much about the Tetons and Jackson Hole. I know you all have had some great speakers who have presented on various topics related to Quaternary geology of the Tetons and Jackson Hole. So in an effort to present something new, I'm actually going to be focused on some of the maybe the less celebrated landscapes that are farther east. And hopefully this all gives you something new and maybe sparks some ideas for future geologic explorations as you explore the landscape around Jackson. Before I get going, I want to acknowledge that this has been a pretty large mapping effort, and it certainly hasn't been completed by me alone. I have my co-authors of these maps listed here. Seth Whitkey is the groundwater GIS and hazards manager at the Wyoming Survey, and he's co-author on all 3 of the maps that I'll talk about. Katie Alexander was our contract mapper for the west half of the Jackson Lake quadrangle in 2020. And all of you who are here probably remember how crazy the summer of 2020 was. Big props to Katie. She was instrumental in helping us have a productive field season through all of the craziness that was that summer. Nolan Barrett was our contractor in 2021 for the east half of the Jackson Lake quad. Both Katie and Nolan now have jobs with the USGS. And then John Krupnick has been our contractor this summer and fall for the current work where we're mapping the west half of the Ramshorn quad. And John's actually a contractor on multiple projects at the Wyoming Survey. And so he has been in the field straight pretty much since July. So major kudos to him for sticking with all these months of field work. I also want to acknowledge that the maps I'm going to talk about today were funded partially through the USGS National Cooperative Geologic Mapping Program, specifically the state map program, which gave us 3 funding cycles to complete this mapping. The state map has funded around 160 maps by the Wyoming Survey since its inception in around 1994. And then finally, I don't have it on this slide, but I do want to acknowledge the fact that the work that we're doing here in Northwest Wyoming, we're really standing on the shoulders of giants, as probably many of you are well aware of. There have been, over the past 100 plus years, some really foundational studies that have been important in our understanding of both quaternary geology and tectonics in this region. Folks like Dave Love, Bob Smith, Ken Pierce, these are true pioneers in the field who without whose work our modern work wouldn't be possible. And a special shout out, as Cynthia mentioned, to Ken Pierce, who over decades of really meticulous field work has shaped our understanding of the glacial dynamics during the Quaternary of the greater Yellowstone area, including the Tetons and Jackson Hole. And the Friends of the Pleistocene field trip this past weekend, I believe, was a really fitting tribute to Ken's legacy. And you'll see as I go through my talk, I'm going to show several figures from Ken Pierce papers and talk about many times where our mapping really follows in his footsteps. So let's take a look at the maps that we've been working on. This is a shaded relief map zoomed into northwestern Wyoming. This bold black line is the Wyoming-Idaho border. And in the thin black lines, I have outlined 30 by 60 minute quadrangles. So these are the maps that we're working on. There are 56 30 by 60 minute quadrangles that cover the entire state of Wyoming. And these 30 by 60 minute quadrangles, they cover a large area. In this part of the state, one 30 by 60 minute quadrangle represents around 1,700 square miles. And so our strategy for mapping these has been to break these 30 by 60 minute quadrangles into halves. So you'll see in the white dashed lines, these are the 3 maps I'm going to talk about. We mapped the west half of the Jackson Lake quadrangle in 2020. We mapped the east half of the Jackson Lake quadrangle in 2021. And both of those maps and accompanying reports are published as open file reports through the Wyoming Survey. You can download those for free at wsgs.wyo.gov. And then this year, we've been working on the west half of the Ramshorn quadrangle. For reference, here we are in Jackson right here. And when we're mapping 30 by 60 minute quadrangles, we're mapping at 1 to 100,000 scale. So that's a little bit zoomed out than most folks are used to. Geologic maps are commonly published at 1 to 24,000 scale. For reference, at 1 to 100,000 scale, 1 inch on the map equals roughly 1.5 miles on the ground. So that gives you a little bit idea of the scale we're talking about. And the maps that I have been working on are surficial geologic maps. And surficial geologic maps are different than bedrock geologic maps. So for surficial geology, we're really interested in the top 1 or 2 meters beneath the Earth's surface. So this means that we're mapping primarily deposits and material, and we're not distinguishing the underlying bedrock units. And by extension, that really means that we're focused on the Quaternary geology. So we're interested in things like glacial deposits, landslides, terraces, alluvial fans, hill slope deposits, those sorts of features on the landscape. And to give an example, this photograph on the right, I took a few weeks ago in the Dunor Creek area north of Dubois to illustrate what I mean by surficial geology. So in this photo, there's a small creek. It's flowing over bedrock here of the Indian Meadows Formation. But on top of that bedrock, you can see there's about 1.5 meters thickness of an unconsolidated deposit, which in this case is a glacial till. You can see a boulder there beneath the tree. So at this particular location, we mapped, the map unit that we mapped was glacial till. And this differs, a bedrock geologist might have come to this very same spot and seen the outcrop of the Indian Meadows Formation in the creek bed and mapped that bedrock unit instead. So for us, we're focused on this top kind of carapace of the Earth's surface for our surficial geologic mapping. So why are we out here doing surficial geologic mapping? Well, first of all, surficial geology is really tightly entwined with the identification of geologic hazards. And in Northwest Wyoming, the primary hazards that we're focusing on for our mapping are Quaternary active faults and landslides. As many of you know, Northwest Wyoming is likely the most landslide prone part of the state. And landslides around here have historically impacted and disrupted major infrastructure. This photo on the left shows Highway 26 crossing an active landslide along the flank of Rosie's Ridge. So this is between the Black Rock Ranger Station and Togwotee Pass. In that whole Togwotee Pass corridor has historically been impacted by landslides and has given WYDOT, the highway department, a lot of trouble. Another reason that we're mapping up here is that the Wyoming State Geological Survey has a goal to complete statewide mapping of surficial geology at 1 to 100,000 scale. So that means completing all of these 56 30 by 60 minute quadrangles. And as you can see in this index map of the state, all of these 30 by 60 minute quadrangles that are colored orange have pre-existing published surficial geology mapped. So you can see that we're getting down to the final few quadrangles here in Northwest Wyoming. And so that's another impetus for our mapping. And then a final factor that's kicked our mapping into high gear is the recent release and availability of LiDAR data. For those who aren't familiar, LiDAR stands for light detection and ranging. And it's a method where a plane flying over the ground shoots laser pulses down and measures the return time of those pulses as they bounce off various features on the Earth's surface. And importantly, with LiDAR data, through several methods, we're able to extract out the overlying vegetation and include only those returns that hit the very Earth's surface. This is called a bare Earth LiDAR model. And so this gives us a high resolution view of the ground surface in the form of a digital elevation model. So this is a data set that we're able to plug into GIS, do a little bit of processing, and come up with products such as this. This is a hill shade. Another useful product is a slope shade. And these are LiDAR data sets are really revolutionary to geomorphology and surficial geology. They allow us to identify landforms at the Earth's surface in great detail that we might not otherwise be able to see because of tree cover, which is really important in this part of the state. So I'm going to show several LiDAR hillshade images throughout this talk, and they'll look like this. This one's actually kind of looking obliquely at a landslide that's actually crossed by Highway 26 just to the east of Togwotee Pass. But you can see the landslide headscarp there and the toe there. So the recent release of LiDAR data, especially in Fremont County, which just came out last year, was a big impetus for us beginning the Ramshorn quadrangle this year. Yeah, for folks on Zoom, the question is, will the Wyoming survey be mapping the Yellowstone National Park quadrangles? And the answer to that is no. And the reason for that is that Yellowstone National Park actually has pre-existing surficial geologic mapping at an even finer scale than 1 to 100,000. Ken Pierce, Jerry Richmond, Henry Waldrop, and others in the 60s and 70s produced really great surficial geologic maps of the entirety of Yellowstone Park at 1 to 62,500 scale. So we're not going to go back and map Yellowstone Park. The existing maps are great quality. Thanks for the question. Well, Gannett Peak's our last one, actually. So that we will map that one. So these white ones are currently unmapped, and yep, you'll see that Gannett Peak is one of the remaining that we haven't mapped. And after we finish mapping on the Ramshorn, our final map will be the Gannett Peak quadrangle. Okay, just a little bit of geologic background. One of the things that makes doing any sort of geologic work in this part of the state really exciting is that we're at the confluence of several different geologic domains. So I've got here another shaded relief index map. This bold black line is the Wyoming-Idaho border. Here we are in Jackson. I've labeled some of the geographic features. So in part of the map area, we have geologic domains influenced by the laramide orogeny. So we have laramide uplifts, such as the Gros Ventre Range, the Wind River Range. This ellipse here is the Washakie Range. And these are mountain ranges that were uplifted between 70 and 35 million years ago, and were uplifted along high angle reverse faults that penetrate the basement rock, the crystalline granitic rocks. And so these are sort of the, as I like to think of the kind of the template upon which all of the later geologic events are built, including, for example, being overprinted by Eocene volcanism. So the Absaroka Range in the kind of the northeast part of our collective mapping area is composed of relatively flat-lying, undeformed volcanic and volcaniclastic rocks that were erupted and deposited locally from vent complexes throughout the Absaroka Range in the Eocene. So specifically around 40 to 50 million years ago. And this Eocene volcanism buries some of the older structures, such as the Washakie Range, which I showed in the previous slide in this area. Then, of course, closer to where we are in Jackson Hole, we have the influence of east-west directed basin and range style extension. And this is responsible for the north trending Teton Fault, which downdrops Jackson Hole relative to the uplift of the Teton Range. And basin and range extension includes many more mountain ranges and basins stretching far to the south and to the east of our map area here. We're really on the, or south and west, excuse me, of our map area. We're really on the northeast flank of the basin and range province here in Jackson and the Teton Range. And then finally, most recently, in the far northwest corner of our map area, we have the influence of Yellowstone volcanism. So this is the track of the Yellowstone hotspot, if you will, which of course it relates to the southwestward movement of the North American plate over the stationary hotspot, which has produced features like the Snake River Plain and most recently in the past 2 million years, the Yellowstone Plateau. And then finally, as an overprint to all of this geologic history, in this region, we have the influence of Quaternary glaciation. So as you drive around Jackson Hole in the Teton area, literally everything you can see on the landscape has in some way been influenced by Quaternary glaciation, so glacial activity in the past 2 million years roughly. So this is the first Ken Pierce figure I'm going to show in this talk. This is oft reproduced and shown figure. This is a map centered here in northwest Wyoming. Here's the Montana-Wyoming border. Here's the Idaho-Wyoming border. And here we are here in Jackson, where I'm shown with my laser pointer. And this map shows in these different colored polygons the maximum extent of glacial ice during the last 2 glacial periods. So in the white polygon here is depicted the maximum ice extent during the Pinedale glaciation, which was the last glaciation, the most recent glaciation to occur in the Rocky Mountains. And depending on where you are in this area, the maximum Pinedale extent occurred between 14 and 24,000 years ago. Then in this red polygon, which you see in places, this represents the maximum extent of ice during the second to last glaciation, which in the Rocky Mountains is termed the Bull Lake glaciation. And from cosmogenic exposure dating conducted by Ken Pierce and Joe Licciardi, we know that the Bull Lake glaciation reached its maximum sometime around 150,000 years ago. Another thing you might notice with this map is, at least for the Pinedale ice, there appear to be sort of two centers or masses of ice in this area. To the south, we have the Wind River Range. So in this area, glaciers originated in the high peaks, the high terrain of the Wind Rivers, and flowed outward across the subsummit surface and down the canyons and valleys to discharge and terminate on the floor of the Wind River and Green River basins, producing the sort of well-expressed and famous sequences of moraine loops that were recognized by geologists over 100 years ago. And that became the type section for the Pinedale and the Bull Lake glaciation. And then farther north, we have this bigger ice mass. This is known as the Greater Yellowstone Glacial System, covering the Yellowstone Plateau, the Beartooths, the Absarokas, and adjacent terrain. And some of you might know this as the Yellowstone ice cap. The term Greater Yellowstone Glacial System and Yellowstone ice cap are pretty much synonymous. But important for where we stand in Jackson Hole, during the Bull Lake period, the Greater Yellowstone Glacial System had a southern lobe that spilled out of Yellowstone and came down Jackson Hole and actually engulfed most of Jackson Hole in ice. The best estimates I've heard is that here in Jackson, ice was as deep as the top of Snow King Mountain. So this was an impressive amount of ice coming down through Jackson Hole. And that southern lobe terminated around Munger Mountain, which is to the south of Jackson Hole. During the more recent, the last glaciation, the Pinedale, ice did not make it as far south out of the Greater Yellowstone system. It terminated closer to the southern shores of Jackson Lake. And importantly, thanks to the great field work and cosmogenic exposure dating of Ken Pierce and Joe Licciardi, we now know that this Pinedale glaciation in Jackson Hole was actually composed of three advances, three separate pulses, if you will, of glaciation that came into this Jackson Lake area. And I'll talk a little bit more about that later in the talk. But for now, let's continue on this glacial geology theme, and I'm going to zoom into our map area, which is this yellow box here. So here we are, zoomed into the map area from that same figure I just showed. And one of the questions that we've been puzzling over and trying to shed some light on the past 2 years in our mapping has related to these somewhat conspicuous question marks on this map, which my eyes have always been drawn to. And this represents sort of the uncertainty of the extent of Bull Lake glaciers in the Gros Ventre Valley and up onto the Continental Divide, extending into the upper Wind River Basin. And so this is something that we focused on the past 2 years in our mapping of this area, trying to tease out this question a little bit. That is correct. Yep, the question is, what do these contours, these blue contours represent? And yes, these contours represent the surface elevation in feet of the ice as constructed by Ken Pierce and Joe Licciardi of their estimate for the ice associated with the Greater Yellowstone Glacial System. Yep. So before I talk about the Bull Lake, just a brief mention of the Pinedale glaciers in this area. One thing that Ken Pierce hypothesized and is certainly shown in his map here is that even during the Pinedale, there was a great thickness of ice, even in the Absaroka Range, covering the high peaks. And from our field mapping and from the recent release of LIDAR data, we've been able to shed some more light on that hypothesis in the observation that we have glacial till that crosses major drainage divides. So documenting the fact that these Pinedale glaciers did indeed cross major drainage divides. An example here, I've zoomed into a LiDAR hillshade of just north of Brooks Lake up by Togwotee Pass. And here we have in the LiDAR really beautiful streamlined ground moraines. If you can see that kind of south-southeast flowing texture below my laser pointer here, that crosses the Continental Divide, which I've noted in this white dashed line near Bear Cub Pass. So this is one of several places where we've documented that ice in Pinedale time did indeed cross a major drainage divide, which speaks again to that great thickness of ice that must have been present in the high Absaroka Range. And this, of course, was hypothesized by Ken Pierce, but it's a departure from previous geologic maps that have been published in this area. So we've been sort of updating that mapping from these previous geologic maps, which were completed largely in the 1960s, that did not show very extensive Pinedale till in this area. So that's been a major kind of change since those maps were first published. Yeah. Yep. Let's see, hide that guy. Aha, perfect. Thank you, Cynthia. Awesome.
Both your maps, areas, are they fully covered with LiDAR?
Hold on one second. Let's see. I need to advance this slide. Oh, there we go. Thank you. Appreciate it. Sorry, John, the question was if our map areas are covered in LiDAR. So we currently have LiDAR for all of Fremont County. We don't have LiDAR for Park County yet. The west half of the Ramshorn quadrangle is probably 75% in Fremont County. So we have 75% coverage for that map. For the Jackson Lake quadrangle, we have pre-existing LiDAR that covers the Grand Teton National Park and a few other areas in Teton County, which probably represent, for the whole Jackson Lake quad, that's maybe a third or half of the area. For the remaining part, there is a gap. For the remaining part of Teton County, we don't have LiDAR yet. And that will hopefully be coming out in the next few years. Okay, let's focus on the Bull Lake here in this area that I'm calling the Gros Ventre Gap. So again, this red shaded area with the question marks on Ken Pierce's map. So this is a shaded relief map zoomed into this area in the red square. Just for reference, some features. This is the Upper Wind River Valley. Here's the Du Nord Creek Valley. This is the South Fork of Fish Creek, which drains into the Gros Ventre River. And this is around where I'm pointing here is Union Pass, if you drive from Du Bois to Pinedale. And we've been investigating this question of what were the extents of Bull Lake glaciers in this area in particular. And we've been focusing on these kind of upper flat upland surfaces, which are kind of have this red tone in the shaded relief map. And we're focusing on this area, one, because there is actually really good preservation of Bull Lake till on these kind of flat rolling upland surfaces around Union Pass, as opposed to in these kind of incised drainages where there really isn't that great of preservation. There's not a lot of deposits on the landscape. And the second reason we're focusing on this area to answer these questions is because there's a really advantageous setup in that there are distinct differences in the lithology of clasts and rocks that are being carried by these two separate glacial systems. So ice coming out of the Absaroka Range as part of the greater Yellowstone glacial system would be primarily carrying volcanic rocks. So things like volcanic breccias and andesites and basalts. Whereas glaciers coming north out of the Wind River Range will be carrying primarily crystalline rocks. So things like granites and gneisses. And this allows us to go into these areas, look for deposits, document classed composition, and come up with sort of a dense network of points documenting where these different clasts are making it to, how thick the deposit is, and any sort of flow indications that we can muster. So I'll walk through a few examples here on these slides. I will show the extent of the Pinedale ice, which is represented by these white lines and arrows, just for reference. So during the Pinedale time, ice from the greater Yellowstone system and the Wind River Range did not meet. And that's pretty well established by field mapping and by LIDAR, where these Pinedale moraines are very clear. And so I'll walk through a few examples here of some of the end members that we've documented of the Bull Lake till. So in some places, we come across a Bull Lake till, and we primarily search for exposures in places like road cuts or landslide headscarps. And in some of these Bull Lake tills, we see a composition that's almost exclusively volcanic rocks. And that's an example of that is this photo here, which is taken from a landslide headscarp just south of Sheridan Pass. The location is shown by this yellow star. And this is a very large, a 3-meter diameter boulder of volcanic breccia that originated from the Wiggins Formation. And the nearest outcrop of the Wiggins Formation to this location is 15 kilometers north in the Pinnacle Buttes area. So if you've ever driven Togwotee Pass, those cliffs off to the north of you are composed of the Wiggins Formation. And that's about the closest outcrop to where this glacial erratic is located. Then in other areas, we document Bull Lake till that contains almost exclusively crystalline rock. So this is an example from the South Fork of Warm Spring Creek, where this Bull Lake till is composed almost exclusively of granitic cobbles and boulders. And then critically, in some areas, we document Bull Lake till that contains both crystalline and volcanic lithologies. This is a photo from a road cut in the Washakie Park area. And if you look closely at the photo, you'll see that there are some light colored rocks and there are some dark colored rocks. This upper kind of right corner is a good example of two boulders sitting next to each other. The dark colored rocks are volcanic, so they're andesites that are coming from the Absarokas, and the light colored are crystalline rocks or granites that are coming from the Wind River Range. And so critically, this documents that during Bull Lake time, ice from these two separate sources was either meeting or at the very least occupying the same area just at different times, which is supporting of Ken Pierce's hypothesis that ice likely met in this area during the Bull Lake time. And so by plotting up kind of this dense network of points that we've established in this area, I can come up with rough estimates of how far north ice from the Wind River Range and how far south ice from the Absaroka Range made it during the Bull Lake glaciation. So in this blue arrow and this blue line here represents the northernmost extent of crystalline clasts that we have documented in Bull Lake till. And likewise, this red line here represents the southernmost occurrence of volcanic clasts that we've documented in Bull Lake till. And so indeed, there is this overlap area where we get clasts of both types that is representing likely this area where those glacial systems merged. And you'll see off to the east and west, I have question marks. I can't really extend these lines further east or west because we don't have the preservation of the Bull Lake till. As I mentioned earlier, we don't have a dense enough network of points to really kind of continue this projection of these ice extents farther east or west. Anecdotally, in the Gros Ventre River Valley, Ken Pierce had hypothesized that most, if not all, of the Gros Ventre Valley was filled with ice during Bull Lake time. Anecdotally, we've documented over the last 2 years several places where there are volcanic lithologies in the Gros Ventre. The farthest downstream that we've found is in the Red Hills area, so just upstream of Lower Slide Lake. And then similarly, there are places in the Gros Ventre where you find granitic lithologies. And these were documented fairly well by Dave Love He called it the Leidy Formation. And we've been to a few of those locations, and sure enough, there's cobbles of granites and gneisses. I was talking earlier with Beverly about the Pack Saddle Pass, and this is a location in the Gros Ventre Range, a high pass at 10,100 feet that sure enough also contains clasts of exotic lithologies, so some andesite and some quartzite from some foreign sources. So there's anecdotal evidence that ice was filling most of the Gros Ventre Valley during Bull Lake time. We just don't have enough density of data points to really say for sure what those extents would have been. Okay, let's shift gears a little bit. And I want to talk about quaternary faults. So on surficial geologic maps, we map only those faults that display surface offset of quaternary age units. So in this part of the state, in our map areas, those surficial units are primarily Pinedale and post-Pinedale deposits. So any fault that you see on our map, you can roughly think of as being active in the last 20,000 years. And the way we go about looking for traces of these faults is to look on the landscape for fault scarps. And these are places where a fault has ruptured the ground surface, producing some sort of topographic step. This photo here is looking at a rather famous fault scarp. This is on the west side of String Lake in Grand Teton National Park. And this fault scarp, which you can kind of see by the shaded step in the ground here, this fault scarp is talked about in an interpretive sign on the Jenny Lake Loop Road. And so, of course, the most significant and largest fault in our map area and in this region is the Teton Fault. We mapped a simplified trace of the Teton Fault on the west half of the Jackson Lake Quad. This is the fault that accommodates the downdropping of Jackson Hole relative to the uplift of the Teton Range and is responsible for the dramatic topographic relief we see on the eastern Teton Range front. I know that there have been a multitude of folks who have spoken in this series about some excellent cutting edge work that's going on the Teton Fault. And so in keeping with the theme of this talk, that's all I'm going to say about the Teton Fault. And let's focus on some of the lesser studied faults that are off to the east in eastern Jackson Hole. So one of these lesser studied faults was kind of an exciting result from last year's mapping. And this is actually a newly documented quaternary active fault. And we were able to recognize it thanks to recently released LiDAR data. We're calling it the Ewell Hill Fault because it crosses Ewell Hill in easternmost Grand Teton National Park. For reference, here's Moran Junction, here's the Snake River flowing south, and here's the valley of the Buffalo Fork as it confluences with the Snake River. And if you look closely into this portion of the LiDAR image, you'll maybe see kind of a dark colored lineament that crosses Ewell Hill here and Spread Creek Hill right here. I'm going to zoom into that area. But the Ewell Hill Fault is about a 4.5 kilometer long, northeast striking, southeast dipping normal fault. And it forms scarps in Pinedale Till and alluvial fan deposits. So I'm going to zoom in right now to this area here. So here's another LiDAR hillshade zoomed into that area. And I've denoted the scarp here with these black arrows, which are pointing to it. So the southernmost extent of these fault scarps are in the Spread Creek alluvial fan. They climb up Spread Creek Hill and cut Pinedale glacial till. Scarps are absent to the west of Elk Ranch Reservoir where there's young alluvium. And then the scarp reappears on the top of Ewell Hill in Pinedale glacial till. One of the unique aspects of the Ewell Hill Fault is the fact that we actually see the bedrock exposure of this fault in the sort of the steep southern exposure of Ewell Hill. And this is actually fairly rare for quaternary faults. Again, for quaternary faults, we're looking for faults that offset surficial deposits. So most of the times when we see a fault scarp, we just see the offset, younger surficial deposits at the surface. But in this case, we can actually see the offset bedrock beneath that Pinedale till at the surface. So in this case, we have offset Cretaceous age units. The Meteetse Formation is down dropped to the southeast against the Mesa Verde and Sohair formations. For reference, total stratigraphic offset here is at least 240 meters based on the thickness of the Mesa Verde Formation. And this bedrock fault was indeed mapped by Dave Love, but he did not show it extending as a scarp in the Pinedale till to the north here or to the south. Yeah. Mm-hmm. It is, yep. And the question for those on Zoom is what is this kind of northeast southwest linear texture on the top of Ewell Hill? And that's a great question, and it leads into my next slide here. In that the other unique aspect of the Ewell Hill fault is that it offsets glacial deposits of two different pulses of the Pinedale glaciation. So if you remember at the top of my talk, I mentioned that from the work of Ken Pierce and Joe Licciardi, we know that during Pinedale time, the ice advanced into Jackson Hole in 3 distinct pulses, which have been dated through cosmogenic exposure dating. And so this northeast southwest streamlined texture in the LiDAR that John was pointing out, which I've shown here by the green arrow, this represents ground moraines or glacial till that were deposited at the bottom of a glacier that was flowing southwest out of the Buffalo Fork during Pinedale 1 time. In contrast, if you look on Spread Creek Hill, you see some of these kind of ropey end moraines and recessional moraines that kind of climb up the north side of Spread Creek Hill. These are moraines that were deposited beneath the glacier in Pinedale 2 time, which was largely coming out of the Pacific Creek area, sort of wrapping around and flowing in this area to the southeast. And so the LiDAR texture bears this out beautifully. And another credit to Ken Pierce, his maps, which he produced before LiDAR was released, all from field work and air photo interpretation, basically show this same pattern. And sure enough, if you overlay those maps on the LiDAR, they match perfectly with what we can see in this LiDAR texture, another testament to Ken's field mapping. But this is an advantageous situation, having glacial deposits of 2 different known ages, which are both cut by the scarp, because it allows us to measure the vertical surface offset of this fault scarp across deposits of 2 different and known ages, which can then tell us something about the rupture history of this particular fault. So to study those vertical surface offsets, we surveyed fault scarp profiles along the length of the scarps through here. And a fault scarp profile is a sort of a 2D slice of the fault taken perpendicular to the strike of that fault scarp. So they give you a sense of the relative offset of the up-thrown block versus the down-thrown block. And I've color-coded these fault scarp profiles. The green ones are profiles that were collected in Pinedale 1 till. The blue ones are fault scarp profiles collected in Pinedale 2 till, and the red were collected across alluvial fan deposits. And we surveyed these profiles both in the field with a laser rangefinder, as well as by extracting the elevation data directly from the LiDAR data set. And so this is an example of one of these profiles. This photo is taken looking to the west at the fault scarp here, which is the step in the topography in Pinedale 1 till. And this profile was taken basically from where the photographer is standing to where Nolan, the geologist in the background, is on top of the scarp and extending well past him. And so this particular profile is shown here. We can plot up the horizontal distance on the x-axis and the elevation or height on the y-axis. And sure enough, you can see the up-thrown and the down-thrown blocks of this fault. And by doing a little bit of fairly simple math, we come up with a vertical surface offset in this particular location of 3.7 plus or minus 0.2 meters. And so by doing this at every place we collected a profile, we're able to come up with some rough numbers of average vertical surface offset. And so the takeaway is that in the older Pinedale 2 till, which dates to roughly 20,000 years ago, the average vertical surface offset of this scarp is 2.5 meters. Whereas in the younger Pinedale 2 till, which dates to 15,500 years ago, the average vertical surface offset is 1.0 meters. So first of all, this pattern makes sense and is to be expected. In a younger surface deposit, we would expect to see less vertical surface offset than in an older deposit, because that younger deposit hasn't been on the landscape as long and hasn't presumably been through as many surface rupturing earthquakes to accumulate that vertical surface offset. It also tells us, making a few very simplifying assumptions about displacement per event, it tells us there has likely been one surface rupturing earthquake along this fault in the last 15,500 years, or since the Pinedale 2 till was deposited, and maybe 2 or 3 surface rupturing events in the last 20,000 years since the Pinedale 1 till was deposited. And these are sort of first order estimates. Of course, to get to the more precise rupture history, we would have to go to this location and dig a paleoseismic trench and do some more precise dating. But this is a good kind of first order approximation. I also want to briefly talk about another fault system that we mapped. This is called the Togwotee Lodge faults. These are farther east from the Ewell Hill faults. And the Togwotee Lodge faults are previously documented. They're in the USGS Quaternary Fault and Fold database. And they're a system of north striking, east dipping normal faults that cross Highway 26 just to the west of Togwotee Mountain Lodge. And they form scarps that offset Bull Lake Till, Pinedale 1 till, and Hill Slope colluvium. And since these faults were previously mapped, and since they are in an area that we don't have LiDAR data, to refine the mapping for our work, we had to kind of do it the old-fashioned way, which meant going out in the field and walking and trying to trace the length of these fault scarps. And it turns out that these fault scarps occur in pretty steep and heavily timbered terrain, so it's not an easy task to trace them in the field. But sure enough, there are places where there are, at least in my opinion, impressively high and fresh looking fault scarps. This is a photo from one of those places. The fault scarp here is this shaded slope in the background. Here's Nolan standing in front for scale. And we surveyed a profile just to the right, off this photo to the right, that yielded a vertical surface offset of around 10 meters. And this 10-meter scarp is near the northern currently mapped terminus of the Togwotee Lodge faults. So it tells us that there's a possibility that this fault system actually extends quite a bit farther north than is currently mapped. We were unable to extend it north in our field mapping. Shortly north of here, the fault kind of dives off into a valley where there's a bunch of young landslides that obscure the fault scarp. But once LiDAR data are available, this fault system needs to be remapped because there's a good potential that extends farther north. So we'll be waiting for the LiDAR data for that. So just a little regional implication wrap up of these faults that we've mapped. The Ewell Hill faults, the Togwotee Lodge faults, the other faults that we've mapped kind of in eastern Jackson Hole are somewhat enigmatic in that we have solid evidence that they've been active in the last 20,000 years, multiple surface rupturing earthquakes in the last 20,000 years. Yet these faults lack a major topographic expression. In other words, they don't bound a range like some of the other famous faults in the Basin and Range. They're not like the Teton Fault or the Wasatch Fault or the Lost River or the Grand Valley. The list goes on of these kind of famous range bounding faults in the Basin and Range province. Instead, these faults that we've been mapping have really subtle topographic expressions. And it turns out we're not the first people to wonder why this is. Of course, Ken Pierce has thought about this in a foundational 1992 paper that he co-authored with Lisa Morgan of the USGS. They hypothesized that there are young or recently reactivated faults which are sort of at the leading edge of a metaphor that Ken used, where he termed it the leading edge of the bow wave, if you will, of uplift on that leading edge of the track of the Yellowstone hotspot. And so that bow wave here is shown in this figure from Ken's 2018 paper, sort of as this parabola-shaped region. And I've circled the faults that we were mapping in yellow here, and they occur within what Ken Pierce terms Belt 1, where the faults are incipient or have recently been rejuvenated. So that's kind of the hypothesis for the origin of the Ewell Hill Fault and the Togwotee Lodge Faults, is that these are on the leading edge of uplift related to the relative passage of the Yellowstone hotspot. And I think it's worth considering and studying faults like these, especially given the recent release of LIDAR data in Yellowstone Park and upcoming in the rest of Teton County, because I think we're going to find more of these types of fault scarps in the landscape that haven't yet been found because they don't bound a major mountain range, yet they're out there in the forests nonetheless. Okay, I'm going to talk a little bit now just at the end here about landslide mapping, the third leg of the stool, if you will. So landslide mapping has been a big priority for us over the past 3 years on these maps we've completed. This is, again, a shaded relief map of our 3 map areas. And all of these green polygons are mapped landslides. And so far throughout these 3 map areas, we've mapped over 2,700 landslides. And that number will continue to grow. We haven't mapped all of the landslides yet in several corners of this West Ramshorn quadrangle. And maybe you can tell even just by looking at this, but one of the takeaways from our landslide mapping, which is true in most places, but I think it's especially true here in Northwest Wyoming, is that landslide type and density are really strongly correlated with the underlying bedrock structure and parent material. So this means that in these different geologic domains, which I mentioned at the beginning of the talk, in these different geologic domains, we get different types of landslides. So I'll walk through a few examples. In the Gros Ventre River Valley, this is a famous place for landslides, as many of you are familiar with. In the Gros Ventre, we tend to see block slides and earth flows. So we get translational block slides in places where there is slope parallel bedding. So places where the sedimentary bedrock dips in the same direction that the slope faces. And we get them especially in areas where there's an interface across which there are rock units of different competence and permeability. The classic example would be a competent and permeable sandstone over an incompetent, impermeable shale. One of these combinations is the 10 Sleep sandstone over the Amston Formation. This is what produced the 1925 Gros Ventre slide. It's also the same combination that produced the Crystal Creek landslide. If any of you have hiked up Crystal Creek, that landslide has been active as recently as 2012. It's really impressive. I recommend you hike up there and check it out. That was also produced via that same combination of rock units. We also get earth flows in the Gros Ventre Valley. In some cases, we get earth flows alone from bentonitic and plastic shales, such as the Maury Shale. In other cases, we get earth flows that are actually as part of a complex with a larger translational block slide or rock slide. Places where that block slide or rock slide, as it has moved down slope, has become saturated and transitioned to an earth flow complex. An example of that sort of complex is here in this photo. This is of the Lavender Slide, sort of where the Gros Ventre Valley opens up around the confluence of Crystal Creek, if you've been up there. The Lavender Slide initiated as a translational rock slide in the Morrison and Cloverleaf formations, up here where I'm pointing, and it transitioned downslope into sort of this broad flowing earth flow that sort of spread out radially. On the right side of this image, this is the Slate Creek slide, and this initiated in the Maury Shale, one of these plastic and bentonitic shales I mentioned, and flows out, sort of changing the course of Slate Creek as this long-running earth flow. This lower photo is looking to the southwest down the headscarp of a large earth flow in dry Cottonwood Creek, which is a little bit further up the Gros Ventre River Valley. In other parts of the map area, we see different types of mass movements. I'm going to focus now on, yes.
Describe, define the different kinds of movements.
Yeah, that's a great question, Cynthia. The question is define the different types of movements. So I should back up a little bit. And when I'm talking about landslides, I'm referring to all mass movements collectively, sort of colloquially. So mass movements can be classified as slides, falls, flows, topples, or spreads. And this is from the work of Varnes in the 1970s. And so all of those, falls, slides, topples, flows, spreads, all of those are encompassed in our landslide mapping. And we usually, when we're mapping these, we will assign an attribute to each landslide, specifying what type it is. And in the case of a complex landslide, that will be, we'll assign multiple types. But to answer your question specifically about block slides and earth flows, a block slide is, or a rock slide, is a translational mass movement where the sliding interface is planar. It's not concave. If it was concave, that would be a rotational landslide or a slump. But a translational landslide occurs on a planar interface across which there's relative motion. There's downward movement of the mass. And so when I talk about block slides, that mass is relatively intact. And when I mention rock slides, that mass has already sort of disaggregated as it's moving down that planar sliding interface. An earth flow is a type of flow that involves finer grain material, and it deforms as a flow. So there's internal deformation, and it includes a relatively high water content, which is what allows an earth flow to have sort of this long running trajectory out into a flat valley bottom, like you see here with the Slate Creek flow. This one here. So this is actually the landslide headscarp. And this is, so again, this is the lavender slide, named for the color exposed here in the Morrison. But this is the headscarp of the translational block slide that sort of initiated that lavender slide, and that later was, with saturation, churned up into more of an earth flow at the base. So yep, that's the landslide headscarp that you can see. This one here. Yeah, and so the main mass probably detached from up here, and this lower section of that cliff is probably more of an erosional exposure more than a landslide headscarp. But certainly this area here is where that translational slide first detached. Yeah, great questions. So another place with different types of mass movements that we've been puzzling over specifically this field season is this area in the southern Absarokas. And when I first put up this map, your eye might have been drawn to this area where these huge green polygons are. It looks like somebody just threw paint at a wall or something. And this is an area in the southern Absarokas where we are seeing some truly enormous slump complexes that span multiple catchments, that include entire valley sides and valley bottoms, and has been really interesting to map in this summer. And so here are just a few examples. It's kind of a complicated slide, but on the left here are photographs from the field, and on the right here are LiDAR hillshade images taken of those same areas. The red stars represent the location roughly where the photograph was taken that accompanies it to the left. But in the southern Absarokas, we see these enormous slump flow complexes that appear to be initiating on an interface that's in the Teepee Trail Formation. So in this upper photo, you see these upper cliffs. This is composed of the Wiggins Formation. These cliffs here are actually the backside of Pinnacle Buttes, the backside that you can't see from the highway when you're driving Togwotee Pass. And there's these large slump blocks that are typically forested below all of these Wiggins Formation cliffs. And from our mapping, we think that what's going on here is that in the underlying Teepee Trail Formation, there's this sort of bentonitic claystone unit, which is probably the detachment or sliding interface upon which all of these slump blocks have detached off of the valley walls of the Wiggins Formation, leaving these huge cliff faces behind. And in this lower photo, this is taken in Ramshorn Basin near the headwaters of Horse Creek, north of Du Bois. You can actually see one of these rotated blocks of the Wiggins Formation that's been detached and incorporated into this slump mass. I've outlined it here with this kind of black dashed line. And then on the cliffs, you can see the kind of in the headscarp, the undeformed flat-lying Wiggins Formation bedding. And so there are several questions that come about from mapping these. First and foremost is the question of, well, when did these enormous slumps occur? And one thing that's clear is that they probably didn't occur all at once. These were certainly catastrophic movements, but it wasn't like the whole valley side came down all at once. We can have a sense of that by looking at the surface topography, which is best shown here in the LiDAR. You can see in this example, there's a region of this slide or slump mass that appears rougher, has a fresher surface texture than this region in the north, which has kind of a smoother surface texture, indicating that this southern sector probably has been active more recently than this northern sector. So they likely didn't occur all at once, but our hypothesis is that these slump complexes were most active during periods of deglaciation. So this would have been in periods when there was a lot of water in the system. And also there was probably sort of a debuttressing effect as ice receded up valley, leaving these cliffs and free faces exposed and susceptible to these large slumps. So that's something that we've been sort of puzzling over this summer, and it has been an interesting mapping challenge, especially in the field, to map these. Teepee Trail. Yeah, so it's a combination of volcaniclastic and pure sedimentary units. It's near the base of the Absaroka volcanic supergroup, and so it's actually really heterogeneous. There are a few beds in the upper part of breccia similar to the Wiggins Formation. But most of it is this sort of tufaceous sandstone and shale. And as I mentioned, there's a few of these kind of bentonitic claystone beds, which seem, our hypothesis at least, those would be the culprit for this sort of sliding interface. Mm-hmm. Like here? Yeah, so the question is, what's this bright white block in the LiDAR image? And that block is actually this block that you can see in the photo. So this is a fully detached, but still intact and rotated mass of the Wiggins Formation that came from up here on the cliffs and slumped down and rotated. And you can kind of see the rotation of the bedding there. So that's that large block in the LiDAR. Yep. Okay, so I'm going to wrap it up here with a few slides, and as sort of a summary. So the talk is titled "Glaciers, Faults, and Landslides." But why do we care? I work for the state of Wyoming. Why is state of Wyoming paying me to go out here and map these quaternary features? Well, first of all, we were just talking about landslides. So one of our recent efforts with the Wyoming survey has been to create landslide susceptibility maps. So these are maps that show areas that are predisposed to landslide activity because of the underlying geologic conditions. And a fundamental input to landslide susceptibility mapping is having an accurate landslide inventory, knowing where there are pre-existing landslides that have already occurred, because it's these pre-existing landslides that really are the most likely places where we're going to see landslides in the future. So having a good inventory of pre-existing landslides from efforts like surficial geologic mapping is critical to landslide susceptibility studies. And the other reason is that actually pre-existing landslides are an input to the landslide susceptibility algorithm that we create in GIS. So we need a sort of a wide census or survey of all landslides in an area in different geologic conditions and different topographic conditions at different slopes and aspects to create that algorithm and to be accurate with it. So that's why we've put attention and detail into mapping landslides that are not just along highway corridors and threatening infrastructure, but also landslides that are deep in the backcountry, because these are going to help us to create that susceptibility algorithm. We're mapping Quaternary active faults because Quaternary faults and their mapped geometry are first order fundamental inputs for seismic hazard modeling. So the USGS creates the National Seismic Hazard Model. This is a product that's updated periodically. In fact, we just went through the most recent round of updates ahead of the 2023 release of the National Seismic Hazard Model. And the National Seismic Hazard Model is important because it sets regulations like building codes. And so the USGS will solicit information from the states. They will come to state geological surveys and say, okay, what is your most recent fault mapping you have across the state? And what are the slip rates that you have for these faults? And so we recently fed all of that data to Alex Hayden and others at the USGS, who have then incorporated all of that into geology inputs that are then fed to the actual modelers who come up with the seismic hazard model. So there's sort of a direct upstream to downstream chain of use of this fault mapping that we're doing on these 30 by 60 minute quadrangles. And then a final reason is that as the state of Wyoming looks to diversify its economy, tourism seems to be becoming more of a focus. And specifically for our agency, we have been collaborating with the Wyoming Office of Tourism on several efforts to promote geotourism throughout the state. One of these efforts was a interactive map of geological highlights to see and features to see on the way to Yellowstone Park. This was released just this past spring for Yellowstone's 150th anniversary. And the stops that are highlighted in this map, some of them come directly from our quadrangle scale mapping, where we've identified and characterized geologic features that the general public would like to see. As all of you know, there's a lot of cool geology to see in this part of the state. So we as an agency want to share that as well. Okay, so as far as next steps, I mentioned that the east and the west halves of the Jackson Lake quadrangle are published. I've printed out the maps and they're up at the front of the library here if you want to check them out after the talk. They can also be downloaded for free from our website, wsgs.wyo.gov. And if you're interested in any more of this information, I would suggest looking at the text reports that accompany these maps. There's a lot of detail in there. And expect the map that we're working on this summer, the west half of the Ramshorn quadrangle, to come out sometime in 2023, probably in May. And with that, I think I'll wrap it up and I'll be happy to take questions. Yeah, Ryan.
So the other day on the Friends of the Pleistocene field trip, we talked about those huge landslide complexes in the northern part of the Tetons, and my students have been mapping up there, and they're just giving us fits because it's like the whole northern Tetons is basically a giant landslide.
Right.
I'm kind of struck by your Absaroka mapping because it looks the same.
Right.
And I wonder, because you guys have worked in the Jackson Lake area and in the Absarokas, we asked this question the other day of Ben Crosby, but you definitely should have been the person we were asking. So I'm just curious if you have any feeling on why some of these places are just completely annihilated by landslides.
Right, right. Well, yeah, that's a good question, Ryan. And for folks on Zoom, the question is about some of the large landslide complexes, which are also present north and west of Jackson Lake, kind of on the northern section of the,
Would you,
of the Teton Fault.
for the Zoom audience, would you repeat the question?
Yeah, yeah. The question is about landslides that are along the sort of the trace of the Teton Fault that's farther north of our map area, in the area that is west and somewhat north of Jackson Lake. Wondering what the cause of those landslides are, and is there any relation? They're sort of similar in scale, at least, to what we've been documenting in the Absarokas. And to answer your question, Ryan, I would say it's probably a different situation in that we have very different lithologic units up there, right? There's no Absaroka volcanic supergroup, there's no TP trail, but as Ben Crosby mentioned in the field trip, I would still say that it probably comes down to interfaces, and we haven't mapped up there, so I don't know the bedrock geology well enough. But in that area, you're starting to get into the sedimentary section, which has some of these kind of problematic interfaces of competent over incompetent or permeable over impermeable. That might relate to that. The other thing that's going on up there, probably related to the Teton Fault, is you have a lot of relief. You have a lot of topographic relief, which sort of sets the stage. But I agree, it's a challenge to map in those sort of areas, especially when you're on the ground, because these mass wasting complexes are just immense, and it's difficult to wrap your head around them. And with if you're in the field without LiDAR data, it's hard to fathom like where they come from, for example. But without having mapped up there myself, that's as best as I can answer that. Yeah.
That new fault that you mapped,
Mm-hmm.
north-south, you related it to Yellowstone, but how do you know it's not part of Basin and Range?
Yeah, that's a good question. The question is about the Ewell Hill Fault, which I was talking about kind of midway through the talk, and I related it to Yellowstone, the sort of the bow wave of Yellowstone uplift. And how do we know it's not related to Basin and Range extension? Well, I think the answer to that question is it's likely related to both. Actually, let me just go back to that figure here. Ken Pierce and Lisa Morgan's idea of this Yellowstone crescent of high terrain and these belts of fault activity incorporates a lot of the famous Basin and Range faults. It incorporates the Wasatch Fault, which is shown here, the Eastern Bear Lake faults, which are shown here. And so it's sort of this Yellowstone hotspot migration, this Yellowstone volcanism superimposed on Basin and Range province extension. And there are a lot of people who have thought about this more than me, sort of the genetic relation of the migration of the Yellowstone hotspot versus Basin and Range extension, and what's the chicken, what's the egg. But I would say that we would probably follow the Ken Pierce's hypothesis that they're actually both interrelated. The Basin and Range extension, the activity or the relative activity that you see along faults in the Basin and Range province, but sort of in this parabola or crescent of high terrain, is related then to that relative northeastward movement of the Yellowstone hotspot. Does that answer your question? Great. Other questions in the audience or potentially from Zoom?
We definitely have some Zoom questions.
Yeah, go for it, Mike.
Yeah, do you believe that the Teton Fault has become inactive? Were most recent earthquakes a reaction to glacial events rather than evidence of continuing uplift? I guess there's really two questions there, but yeah.
Yeah, that's definitely not my wheelhouse. And there are certainly people who have thought about this more than me. But we had some very lively discussions about the activity of the Teton Fault and what it potentially means on the field trip this past weekend. I would say that in my opinion, the Teton Fault should be classified as an active fault. It's been active in the Holocene, and there's great paleoseismic evidence supporting that. And then the second part of the question about glacial activity potentially being a causative factor in movement along the Teton Fault. That's also something.
Well, I think
was that the question?
I'm not sure that's. Well, I'm not quite sure. Let me just rephrase it and do it again. Were most recent earthquakes a reaction to glacial events rather than evidence of continuing uplift?
Okay, were most recent earthquakes result of glacial events rather than continuing uplift? Yeah, right. And that is a hypothesis. Our mapping can't shed light on that question, I don't think, but that is a hypothesis of some folks, is that the unloading or the isostatic rebound, specifically related to the greater Yellowstone glacial system, may have caused a period of activity along the Teton Fault. We've had great discussions about that on the field trip this past weekend. And one thing I'll just say is that the timing for that doesn't necessarily match up, in that we see in the paleoseismic record and in studies of the relative offset along the scarp in deposits of different age, we see this kind of recurring pattern that the Teton Fault had a period of relative activity from the period of about 20,000 to 14,000 or 12,000 years ago, which would have been a time when there was still a lot of ice in Jackson Hole, and the greater Yellowstone system, in fact, was at its maximum. And that after that period, there have been less events recorded, at least in the paleoseismic record. So the timing for that does not perfectly match what that hypothesis would suggest. But that's again, our mapping can't really shed light on that. So that's all I can say about that. But I would there's other people who have really thought about this, and some of which have actually given presentations in this series, who I'd recommend watching their presentations to get a better idea of that.
Okay, well, here's another one. Where do you feel? Do you have any feel for where all the placer gold in the Snake River gravels comes from?
No, that's not my wheelhouse either. Although
Either. Okay.
The only, yeah, Mike. The thing I can say about that is that in both the glacial outwash deposits in Jackson Hole and in the modern day Snake River, you see a predominance of quartzite, rounded quartzite cobbles, which are primarily coming out of the Pinion conglomerate, which it covers an extensive area well, they're called the Pinion Peak Highlands, this area that's north of the Buffalo Fork, east of the Snake River, but still west of the Absaroka Range and south of Yellowstone. In that large region, the Pinion conglomerate is the dominant lithology, and Ken Pearson, his studies of the glacial features of Jackson Hole on the outwash, recognized that almost all the cobbles that you see in glacial till and outwash in Jackson Hole from deposits that have come south from the greater Yellowstone glacial system are carrying these resistant quartzite cobbles. And interestingly, Dave Love spent a lot of time studying and measuring section in the Pinion conglomerate, from what I can tell, primarily because it is gold bearing. In fact, in almost every publication, Dave will, he prefaced Pinion conglomerate with gold bearing Pinion conglomerate. So I don't know if those two things are connected, but that's an anecdote. Other than that, I'm not sure, Mike.
Okay, and here's a final question. It says, to my naive eyes, a slump could look like a fault.
Yes,
I guess
absolutely.
yes, yeah.
It's not I think any geologist struggles with that. There's a gray area, right, between what we call, you know, tectonic faults and mass movements. There's certainly a gray area, and especially in the field, it can be difficult to distinguish those two.
Okay, well, okay, there's one here that just came in. Okay, summit of Mount Leidy appears to be pinion conglomerate. Yes, no?
Yes, that's correct. Yep, Mount Leidy and most of the Mount Leidy highlands are pinion conglomerate, correct.
Okay.
The pinion is Cretaceous to early Paleocene, and so it reflects sediments shed. So from my understanding, and the question for those on Zoom is the question was the age of the pinion conglomerate and where the cobbles are coming from. And so those cobbles are all quartzite cobbles, and they were shed off of the ancestral Gros Ventre River uplift, one of these laramide uplifts, and they were basin filling sediments carried by rivers flowing to the east in the northeast, and then, you know, buried and cemented as the pinion conglomerate.
Well, that's it. I really enjoyed your talk, by the way. You're very clear, and you're precise, and very well, you know. Anyway, it was very interesting. Thank you so much.
Yeah, thanks, Mike. And it looks like we have maybe one more question in the room here. From unloading from the ice sheets. Yeah, and there various authors have cited evidence for that. In fact, one piece of evidence, again, this isn't my expertise, but one piece of evidence is in the pattern of river terraces and outwash terraces as you go downstream in Jackson Hole. The fact that river terraces actually sort of project and converge in the downstream direction. This has also been documented even farther downstream in Jackson Hole in places like Alpine Canyon along the Snake River, actually by a group at Utah State with actually my master's advisor, Joel Pedersen, who I believe has given a talk in this series. But that folks have cited that sort of evidence as signatures of isostatic rebound in the Yellowstone Plateau area. Yeah, that would have been that. Well, some would say, though, continuing into the modern day. I mean, geologically speaking, it was not that long ago that we had, you know, massive volume of ice covering the Yellowstone Plateau, as recently as 15,000 years ago, approximately. So some folks would say that isostatic rebound may even continue today. Depends on who you ask.
Another quick question. It doesn't seem there are any esters. Why is that?
Yeah, the question was about eskers. I believe actually there are eskers along the southern shore of Jackson Lake at South Landing. If you look in the Ken Pierce 2018 paper, I think he documents some esker-like features in just south of South Landing. The reason they're not more prominent is probably topographically related. Again, eskers are a feature that we see very, very commonly associated with the large ice sheets that were coming out of Canada. So like the Laurentide ice sheet, for example, in places of fairly uniform topography where those meltwater channels could become established and long-lived features. Whereas in Jackson Hole here, Again, the ice was much more confined by topography, and there were probably more internal dynamics going on within that glacier that prevented these long-lived meltwater streams from establishing. And then also the fact that we've had recent overprinting from multiple pulses of glaciation and subsequent glacial outwash that has largely buried a lot of the primary glacial features here in Jackson Hole. Any other questions?
I have a question.
Yeah, Cynthia.
Do you have any examples of how this type of mapping has changed decisions about building infrastructure or buildings?
Not any direct examples I can think of off the top
I'm sorry,
of my
question.
yeah, sorry,
repeat.
Mike. The question was, are there any examples of this type of surficial geologic mapping changing decisions about where to site infrastructure and that sort of thing? And my short answer is I can't think of an example off the top of my head. I've been with the survey for 4 years, and so I don't go back a long way. I will say that we have worked closely with land managers during these mapping efforts. My first year at the survey in the summer of 2019, we mapped the surficial geology of 2 7.5-minute quadrangles at 1 to 24,000 scale in the Gros River drainage in the Wyoming range, specifically the Blind Bull and Pickle Pass quadrangles. And these were places where there had been landslides the previous season that had taken out forest roads. And so in that map, we worked closely with Bridger-Teton National Forest and shared with them our mapping, which informed sort of how they open those roads. It didn't necessarily inform them citing new infrastructure. They weren't looking to build anything new, but it did inform their management of those roads for the sequential seasons afterward.
Certainly hope that surveys every time I drive down the back,
Yeah.
sure they think that road's gonna stay.
Yeah. The comment was about our interactions with YDOT, the state highway department, and we do work with them, and we share all of our information. So they definitely have our surficial geologic maps, and I can attest that YDOT has some very good geologists working for them. We've done field exercises, and they've got their own geology division that focuses on this sort of thing. So they're in tune with it for sure.
I have a couple more questions. I don't know. Your talk has sparked a lot of questions. So here's one. People were just interested in the mix of your work, the time mix of your work. Like, how much time relatively do you spend in field work, lidar interpretation, and preparation of maps?
Yeah, that's a great question. For field work, I like to get out in the field for 6 solid weeks a summer, and so that's what we've done for the 3 maps that I've shown from the past 3 years. So apart from that, a lot of our mapping, especially for these 30 by 60-minute quadrangles, is based in the office, interpreting lidar, interpreting aerial photos. These maps are such a huge area to cover that we can't possibly see every place in the field. So for the more remote areas, we're going in and mapping off of lidar and then field verifying. In some of these kind of focus areas, which I highlighted in this talk, we're doing more primary field work. But as far as the balance, 6 weeks a year in the field, the rest of my year is in the office, spent either mapping or writing reports. And I also have other projects that I work on other than these surficial geologic maps.
Okay. All right. Well, I think that should do it for us at this end. Again, thank you so much for extremely interesting and well presented talk.
All right. Yep. Thanks, Mike.
Great, so much. As customary with our speakers, I would like to present you with a very small token of our appreciation.
Oh, thank you.
Geologists of Jackson Hole.
Yeah. Thank you so much, Cynthia. Appreciate it. Awesome. Great. And thanks everybody for tuning in via Zoom.
Now, remember the drill on the cheers, please. Right here. Don't forget to tell everybody speak.
Excellent talk.
Yeah, thank you.
I think this is done. I'm just going to end the talk. Okay, Elizabeth, I guess you're all set on your end. Oh, okay. No, I'm talking about to Elizabeth. Okay, I'm going to end this talk. Hopefully that works for you.
Good night.
Good night. All right. Thanks so much. All right. Bye now.